Okay. Was that snow out day the last week before spring break?
Yeah.
So we missed,
A
so,
lab.
so half of the class has missed a lab
Correct.
and half has done it. Okay,
Correct.
okay. I can work with that. And, then we were gonna do the quiz on Wednesday too. So let's do the quiz this Wednesday.
Perfect.
Okay, it feels like this quiz has been building up and building up. It really is not that big a deal. So quiz one is, it's going to be at the end of class on Wednesday. And to get ready for the quizzes, all you need to do is just skim through your notes, remind yourself of the big ideas. I'm going to ask you short answer questions about those. Yes?
So the quiz is going to be on everything?
Everything, yeah.
Okay.
Yep. And actually, every test and quiz that I give is on everything. So remember to always go back all the way to the beginning as you're studying for stuff. But I think the most effective way to do it, I mean, I know like schedules get in the way and stuff, but the most effective way to do it would be to just once every couple weeks, just go back and skim through your notes, just to the point where you start to recognize like, oh, I know what comes next. I know this says this. I know, that's what you're trying to get to. That's what I'm trying to get you to, I'm trying to make that your goal, just so that you remember the stuff better. Okay, and of course, we'll have probably a total of 4 or 5 quizzes for the semester. They add up to a total of 5% of your grade. So each one is, say, like 1% of your grade or something. It's not a very high stakes thing. Anybody have any homework questions you want me to go over? Okay. Well, we are pretty much done with particle kinematics now. The next topic is particle kinetics. So remember, kinematics is just relationships. So I said that it's really just carefully describing motion, kind of. Describing. And that means you're finding relationships between time, position, velocity, and acceleration. So now with kinetics, we're still dealing with all of these old things, but we're adding the causes of the motion. And those are mass, force. Those are the ones that we're going to deal with now. Later we'll talk about energy. I wrote this wrong. It's confusing enough without me doing that. Kinetics. So the longer word is the shorter subject. The shorter word is the longer subject. And so the first thing I have to do before we can, so what we're going to get into with kinetics eventually is relationships between these causes and the motion that they produce. Before we can do that, I have to define these two new things. So first I'm going to define mass and force. And I'll start with mass. That's kind of the easier one. In everyday life, you sort of get the mistaken impression that weight and mass are the same thing. You tend to think of pounds as a measure of mass, and then your scale has a setting on the bottom. You can flip a switch to go between kilograms and pounds. Well, pounds is a unit of force. It's a measure of force. Kilograms is a measure of mass, and they're different things, although they have a close relationship, but they're different things. So don't think of mass as equivalent to weight. Okay, like on your scale can measure your weight, or your scale says it can measure your mass. It really can't measure your mass. What mass is a measure of an object's resistance to acceleration. So something that has a big mass, it's hard to make that thing accelerate. It's hard to change its velocity. Something with a small mass, it's easy to change its velocity. It's easy to make it accelerate. This comes up in football. So here's a football drawing for you. Okay, so here's one football player, and now here's the other one. Yeah, it's going to go just super horribly for this one guy, no matter how determined he is. Okay, so when these two players run into each other, they're going to exert forces on each other, and the one on the left has a large mass, a high mass. That means this person is very resistant to acceleration. This person has a small mass and therefore a low resistance to acceleration. And so when they collide, the force of their collision is not going to change the big person's velocity very much. That person's going to sort of just keep moving in the same direction, be slowed down a little bit. But the person on the right, their velocity is going to change very quickly, which is equivalent to having a very high acceleration. Depending on what this person's mass is, this person might end up going exactly in the opposite direction that he's running in this picture, And so that's the effect of mass. And, that's a reason why football coaches, all things being equal, would rather have somebody with a lot of mass, It's hard to change their velocity. The SI units of mass are kilograms. And one thing to notice about this, we've been talking about vector quantities, but notice that mass is not a vector. It's just a positive number. So there's no such thing as having mass in a certain direction. It's just a property that you have, it's directionless. And that's about all I have to say about mass. But remember this definition of relating mass to how hard it is to make something accelerate. For like astronauts and space stations and stuff, it's really easy to lose muscle and bone density when you're, living in a space station. And so they need to have their mass measured all the time to see if they're losing, muscle, bone. And now I said that there is a pretty close connection between mass and weight. And if you're on a planet, which we are, then a certain mass always corresponds to a certain weight on a scale. So that's why your bathroom scale tells you that it can measure your mass in kilograms. Your scale's circuitry is assuming that you're roughly at sea level on the Earth, and so that it can estimate the strength of gravity, and it uses that along with your mass, along with the force of your weight that it feels to estimate your mass. But if you took like a bathroom scale to a different planet or to the moon or something, where the force of gravity is a lot less or a lot more, your scale would still be correct in the pound setting about how many pounds of force you're applying to it, but it would be drastically wrong at guessing what your mass is, because it's still making this assumption that you're at sea level on the surface of the Earth. So for people, and then if you're on a space station, you're even a step worse off than that. Bathroom scales don't even work. There's no gravity at all. So how do you measure the weight of somebody basically, essentially in space? This is sort of a funny thing. Did you know this? That like on space stations that are orbiting the Earth, all the pictures and videos you see, it looks like people are weightless. And it is true that if you get really far away from all the planets and everything, there is true weightlessness. But if people are in orbit around the Earth, the reason that they're in orbit is because gravity is making this thing turn. So you're really not weightless. You have apparent weightlessness because you're falling, you're in free fall, but the thing you're in is in free fall around you too. And so basically you're both just falling the whole time. But since everything's falling with you, it seems like you're just hovering there. So that's kind of different. Like if you in fact somehow did manage to get way out far away in the galaxy, where far enough away from things that there is such a thing as really not being affected by gravity. But people in orbit, that they're not that. And on the moon, you're not that, Oh, no, so I didn't finish what I was saying though. So if you're on a space station and you want to measure your mass, you can't use a scale the way we think of scales because there's no gravity. What they do is they actually apply known forces to these people and then calculate the acceleration that's produced by these forces. And so it's really using the definition of what mass is. If a given force leads to a larger acceleration than it did yesterday, then you've lost mass. If it leads to a bigger acceleration, then you've gained mass. Okay, that's everything for mass. So now we're going to talk about force, and that's a little bit more complicated to talk about. And the definition I'm going to use, I'm going to say force is a vector that measures the intensity and direction of a push or a pull. On an object. Okay, so mass was not a vector. There's no direction associated with mass, but force is a vector. You know, mathematically we represent something different if it pulls you this way than if it pulls you with the same amount of force but in the other direction. That direction matters. The units for force are kind of complicated. It's units of mass times units of length divided by units of time squared. And so in SI units, this is kilogram meters per second squared. But force is one of the most important quantities that we're going to deal with. And so since this is a pretty cumbersome set of units to deal with, we give it its own name, the Newton. And I'll abbreviate it with a capital N. So 1 kilogram meter per second squared is 1 Newton. In this class, there are only 2 ways that forces will arise. The first one is weight. And weight is the force applied to an object by gravity. And then the only other way that forces are applied is through contact with the boundary of an object. So there really are some other types of forces. We're just not going to talk about them in this class. They really fit into the category that weight fits into. Those are called field forces or conservative forces. It's like force fields, but like superhero shows or whatever make force fields seem really cool. They can be pretty boring. Weight is a force field. We'll talk about it more, what that means, when we start talking about energy. But some other types of field forces would be like magnetic field forces can apply. Magnetic fields can apply forces to certain things. Electric fields can apply forces to certain things. Anybody here who takes physics 2, you're going to deal with that stuff there. But for now, weight is the only field force that we'll have. And the only other way that forces can be applied is by actually making contact with the boundary of the object. And the big equation, this is the most important equation in this class. And it's the equation that relates force and mass to kinematics. So like what kind of motion is produced by a certain force and a certain mass, that comes from this equation. The equation is called Newton's second law. And when I write this, I'm going to abbreviate it N2L, Newton's second law. And Newton's second law says F net, a vector F net, is equal to m times the acceleration of the center of mass. So maybe you've heard that before, F equals ma. That's what Newton's second law is. And I'll tell you what each one of these variables mean. So F net is the sum of all the force vectors acting on the chosen object. M is the mass of the chosen object. And ACOM is the acceleration of the center of mass of the chosen object. Well, remember that when we're doing particle calculations, we're always assuming that the object only exists at its center of mass. So in other words, this acceleration of the center of mass is just the acceleration of the object, the way we've been considering it. But like, what does that mean? Like, if I throw this stapler up into the air without spinning it, then every point on this stapler would have the same acceleration. And while it's in free fall, that acceleration would just be 9.81 meters per second squared down, okay? But if I did it again and spun it, okay, every point on this object would have a different acceleration as it spins. Can you imagine how? And so this equation wouldn't necessarily hold. It depends what point you're looking at. But if you track the motion of its center of mass, like if you drew a red dot where the center of mass is and track that, that point would have an acceleration down of 9.81 meters per second squared. Okay. All right, so the first thing we have to figure out is what the force is that's applied by gravity. What's the weight force? So weight is the force applied by gravity. So to do this, we're going to make the assumption that no matter what an object is doing, gravity applies the same force to it. That's kind of a leap of faith, you know, but it probably makes some sense to everybody. And it turns out that it's true. So we're going to just assume that gravity always applies the same force to an object no matter what the object is doing. And now we're going to think about a 1 kilogram object in projectile motion. Okay, so it's going to travel some kind of parabolic path depending on what direction it was launched. So it'll follow a parabola like that. Now I said that the only way that forces can be applied to an object are through weight or through contact with the boundary. For something in projectile motion, if we're ignoring air resistance, like we usually do, like we always do, the only force on this object is gravity. So the only force on the object is gravity. We know that because it's just not in contact with anything, okay? We also know that the acceleration of the object is 0, negative 9.81 meters per second squared, as long as our y-axis is pointing up. So let's say we're using a coordinate system like this. Okay, so anything in free fall or projectile motion, that's always its acceleration. So now let's put it into Newton's second law. So Newton's second law says the gravitational force, call it F grav, that's the only force acting on it. So this is all the, this is the sum of all the forces acting on the chosen object. And that's equal to the mass, 1 kilogram, times the acceleration vector of 0, negative 9.81. And so this gravitational force is equal to 0, negative 9.81. And this is kilograms times meters per second squared. That gives newtons. So while this thing is in projectile motion, it has a downward force of 9.81 newtons acting on it. Okay? So you might think, it seems like a reasonable first guess, like I've seen that 9.81 before with accelerations. Everything in projectile motion has an acceleration of 9.81 meters per second squared down. So maybe every object has a force of 9.81 newtons acting on it. So now let's do the same thing with a different mass, okay? So this time, let's say a 10 kilogram object. Okay, again, the only force is the gravitational force. Do we know what the acceleration of this object is? We do. For anything in projectile motion, no matter what its mass is, the acceleration is down at 9.81. Remember the bowling ball and feather thing. So this is 0, negative 9.81 again. And now I'll plug it all into Newton's second law. And we get that the gravitational force is equal to, okay, this time the object's mass is 10. So 10 times the acceleration, which is 0, negative 9.81. And so this time the gravitational force is 0, negative 98.1 newtons. Or if I want to show the direction, it's a downward force of 98.1. Okay? So what you see here is the weight force depends on the mass. And that gravitational force is always downward with a magnitude of the mass times g, where g is 9.81 meter per second squared. Okay, so this is sort of a sticky point, but see if you can keep this straight in your head. So if I asked you if gravity makes heavier things fall faster, the answer is no. Okay, that's the bowling ball and feather video. But if I asked you, does gravity pull harder on heavier things? The answer to that is yes. And the way that those work with each other is, remember, mass tells you how resistant something is to acceleration. So if you're trying to get something that is really good at resisting acceleration to accelerate down at 9.81, you have to apply a bigger force to it. Okay, so gravity pulls harder, but it pulls harder in exactly the right ratio for the accelerations in free fall to be exactly the same. Okay. Okay, so how does a bathroom scale work? Okay, so let's I wonder what year I first drew this guy like this. I've gotten really fond of this guy. His shoulders are always uneven, but in his little tank top, looking so unhappy with the whole process. Okay, so let's say that this guy has a mass of 100 kilograms. And let's say we want to know what's the force applied to the man by the scale. Okay. And so if you think about a scale, it's kind of, it seems a little weird that it's like, how is this thing measuring how hard gravity is pulling on you? This thing doesn't have anything to do with gravity. Gravity pulls on the scale itself, but it can't measure how hard gravity is pulling on you. And the only thing touching the scale, I guess there's the floor and then there's your feet on it. So let's figure out the relationship between what the scale, the force the scale applies, and the weight of the person. So the chosen object is going to be the person, the man, and there are two forces acting on the person this time. There's the weight force and the force on the man by the scale. Okay, so there's a total of two. Okay, and now what about the acceleration? It's not free fall. Remember that zero acceleration is the same as constant velocity. This person's velocity never changes. He's just standing there. So the acceleration is zero. Okay? So now we can start to put this stuff together into Newton's second law. I'm going to say that the forces are, there's the gravitational force. And then there's the force from the scale. That's all the forces. And this is equal to the mass times the acceleration, that's 0, 0 in this case. Now I can fill out what we know about the gravitational force. This gravitational force is down at 100 times 9.81. And so I'll write that as 0, negative 981. Plus Fs is equal to 100 times 0, 0, just gives you 0, 0 again. Okay. So now we can do the algebra with these vectors. You could break it up into x and y components, or you could do the algebra with vectors. I'm going to think of it, I guess, as like 0 plus the x component of this force is equal to 0, and negative 981 plus the y component of the scale force is equal to 0. And so this says that Fs x component is 0, and Fs y component is positive 981 newtons. And so that force that's applied to the man by the scale is 0, positive 981. Or you could also think of that, that's in the positive y direction. So this is an upward force of 981 newtons. Okay? So what we figured out from this analysis is that as long as there's only two forces acting, the weight and the scale on the man, and as long as the acceleration is 0, that scale has to apply exactly the force equal to the man's weight. Okay, so that's how a bathroom scale, it can tell how much force it has to apply to the person, and then that's what it assumes is the weight. Okay? So what if you brought a bathroom scale on an elevator, say? This is
Funny.
You should, well, now do it. This is, well, what you have done is you have noticed that if you stand on a scale quickly, I don't know. Does this work with digital scales? It probably doesn't. On the old days when the scales were like dials, if you got on too fast, it would like oscillate back and forth until it settled at the weight. And what's going on there is when you first get onto it, there's an acceleration that's not equal to 0. And so things are kind of changing around. It's sort of the same effect as being on an elevator. So let's say that, so we have a man and a scale in the elevator. And let's say that there's a downward acceleration of 2 meters per second squared. Okay, so first of all, when an elevator is going up or down, is it always accelerating? No, right. Most of the time when an elevator is going up or down, it's going at a constant velocity. But right at the start of the motion, as it's going from being at rest to going up, or starting at rest and then going down, it's briefly accelerating. So that's what we're looking at here. We're talking about just that half a second or whatever, 1 second, where you're going from rest to going downwards. Okay? Or it's equivalently, it could be when you're going up and it's just as you're coming back to rest. It has the same effect. A second. Okay, so there's the elevator. Whoa. Here's the man. He doesn't seem like the kind of person who would bring his scale on the elevator, but so this is accelerating down at 2 meters per second squared. And now we want to know what's the force on the man by the scale. Okay, so the things we know that the weight force, the gravitational force, is 0, negative 981. We know that the acceleration this time is 0, negative 2. And now we'll go to Newton's second law. The only two forces, there's the force of gravity, and then you can just think of going around the boundary of whatever the chosen object is, the man in this case, looking for where the surroundings make contact with the boundary. And the only place is at the scale. So we have 0, negative 981. Plus the force applied to the man by the scale is equal to 100 times the acceleration of 0, negative 2. And now you can do the math. You have 0 plus fsx is equal to 100 times 0. So fsx is equal to 0. The y equation says negative 981 plus fsy is equal to negative 200. And so solve for this, and you get that fsy is equal to positive 781 newtons. Okay, so in the case of the elevator accelerating down, the scale reads a lower, it's not really a weight, but it reads a lower force. It calculates a lower force. So 0.781, or in other words, an upward force of 781 newtons. So was anybody in here ever a wrestler in high school or anything? Like, yeah, this is if you still have any eligibility, because this is a really good trick. Like if you're ever at weigh-ins, you're overweight, just convince them that you're like in a hurry and they have to come measure you on the elevator. Okay? Like you can cut 20 pounds just like that. You can wrestle in like the 70-pound division. Okay, and then, yeah, if it was accelerating up, then the weight would go up. It's just the way the algebra works out. Okay, well, you can see that, so we started out with a simple problem where the only force was gravity and it was pretty easy to work with. And then we added a second force, and you can see how, like, as you start adding more and more forces, it would be nice to have a bookkeeping approach. And so we're going to get into things where there are multiple forces acting on objects. And so the next thing I want to talk about is a bookkeeping tool that we're always going to use anytime we use Newton's second law. And that's free body diagrams. And when I abbreviate this, I'm always going to just call it FBD, free body diagram. And you need to draw a free body diagram. Every time you use Newton's second law, there's one exception to this, unless you are just calculating the net force. So there are some questions that'll ask you for the net force, just the sum of all the forces. In that case, a free body diagram isn't going to help, and you can just skip it. But here are the steps for drawing a free body diagram. So first, draw a closed outline of the chosen body. And that outline should have no external objects. And no internal details. Okay, so for example, if this is your chosen object, it's This man that I like so much standing in the grass. So what does a free body diagram outline look like? Something like that, okay? That's a closed outline. There's no internal details, no external objects. So here are some that not to do, you know? So the first one is this. Don't do this because that's not an outline, okay? What we're trying to do with this is we're trying to be as clear as possible about, we're separating the universe into two things, the stuff inside the boundary and the stuff outside the boundary. That's why you want to have that closed outline, you know what I mean? So this is not an outline. This one isn't good because he doesn't smile like that. This has internal details, no internal details. And then the last one is you don't want to do this because that has external objects. Like it can just be confusing. Like, are we talking about, do we have to account for forces on that grass, on that ground that he's standing on now? We want to just be, we don't want that in there because we just want to be absolutely certain what is the boundary that we're dealing with. Okay, so this is the one we want. Yay. Step 2, draw a downward facing arrow. This represents the weight force. And label it either with mg or the numeric value of mg if you already calculated it. So for example, in this case, you can do this or this if he's still 100 kilograms. I guess I usually don't put the units on here, it just makes it a little more cluttered. I'd leave that off. Oh, wait, he's standing there. So I'm missing, oh no, that's what I said to do, sorry. This is step 2. Okay, and then step 3. At each point where the surroundings contact the boundary, draw an arrow in the direction of the force. in the direction of the, let's say, the contact force. And I'm going to, probably the next class, but pretty soon I'm going to tell you all the rules to follow for how you know the directions of the different forces. Draw an arrow in the direction of the contact force and label it with either a value or a variable. If you know the value, you can put that in. Usually it's something you'll have to calculate. So label with a value or a variable. Okay, so for this example, we have the weight force like this, and that is 981 newtons. And then we haven't talked about why this is yet, but the ground is going to be pushing up on the man. So that force is this direction. And we don't know the value of that force without doing a calculation. So I'm just going to label that N stands for normal force. But remember that that's just a variable. You could use R or F or whatever. One thing you should notice is I'm going to use this normal force symbol pretty often. And obviously I'm going to use newtons pretty often, and they're both capital N's. So whenever I use N as a normal force, I'm always going to represent it as a fancy N with a hat and tails thing, shoes and hat. So if it doesn't have the two little serifs, then it's newtons. And if it does, then it's a variable representing a normal force. Okay, what's the point of a free body diagram? So here's the thing to notice about it. If you do your free body diagram right, it gives you everything on the left side of Newton's second law. So then, once you have your free body diagram, really all you have left to worry about is the mass times acceleration part of the equation. Okay, I think we have time for one thing here. So I'm going to break up contact forces into 3 different types. The first one is pushing forces. The second one is pulling forces. And the third one is friction forces. And I'm just going to go through these one by one. Today I'll talk about pushing, and then we'll stop, and then we'll do pulling and friction on Wednesday. So the first one is pushing contact. So a pushing contact applied by the surroundings, you can think of it as preventing the chosen object from invading its space. Okay, so like if I push against the wall, it's applying a force to my hand that's keeping my hand from sinking into the wall, okay? So, and another way you can think of it is like, okay, if you're wearing like a puffy coat, just think of like pushing and pulling, what direction does the coat go, you know? If someone pushes your coat, it goes towards you, that's the direction of the force, okay? So pushing contact is always toward the chosen body. Perpendicular to the surface. Okay, so for example, let's say we have these two carts. And I guess I'll give them some masses. Let's say this one's 20 kilograms and this one's 40 kilograms. And let's say that there is a 50 Newton force applied this way and a 100 Newton force applied this way. And we want to draw a free body diagram of each cart. Okay, so I'm going to start with the 20 kilogram. So step one is we draw a closed outline of this body with no outside objects and no internal details. So there's the outline. Step two is we draw the weight force. The weight always acts at the center of mass, so that's why I always sort of roughly put it in the middle. So we have a downward force of 20 times 9.81. That comes out to 196.2. And now we just go around the boundary looking for places where the surroundings make contact with the boundary. Okay, the first one is this 50 is applied to the boundary, so I'm going to put that here, and I don't really have to change anything there. That's already given as a force. And the only other places where there's contact with the surroundings contact the boundary is here at the wheels and here where the two are pushing on each other. Okay. So at the wheels, since we're still doing particle stuff, I'm not going to draw separate forces on both of these two wheels. I'm just going to put it at one spot. But let's think about the rules for a pushing force, okay? First, you know it's a pushing force because the ground here is keeping this cart from invading its space, from sinking into the ground. So we know it's a pushing force. The direction is perpendicular to the surface toward the chosen body. So that means this way. Okay. And we're just giving it a variable name. I'll name it N20 for normal, the normal on the 20. And then if we keep going around, we get to this other pushing force. And so this is perpendicular to the surface toward the chosen body. And people often use, for a force like this, the variable R for reaction force. And so that's it. Now we dealt with the weight force. We dealt with everywhere the surroundings contacted the boundary, so we know we're done. You know, there's no ambiguity about whether you're done or not. And now I'll do the 40. The weight force is 40 times 9.81, so 392.4. On the 40, notice that, you know, the 50 doesn't act on the 40. The 100 didn't act on the 20, so it doesn't show up here. Even though the thing that can get confusing about this is like, both of those forces definitely affect the motion of this whole system. There's no doubt about that. But you're only putting in the forces that make direct contact with the boundary of your object, okay? And we'll see that it'll work out where even though, like say we use Newton's second law over here, and it doesn't have the 100 in there, we're gonna see that we can get the right answers this way. Okay, so we have the 100 here. We have a pushing force over here, so the rule says it's perpendicular to the surface toward the chosen body. And I'm going to do one thing here that we'll talk about little by little as we go, but notice that this R is the pushing force on the 20 by the 40. This pushing force here is on the 40 by the 20. If all you're doing is switching that, that causality between two objects, you know, if you have a pair pushing on each other and you're just switching which one you're talking about, use the same variable for that. Those will have the same value. Okay, so I'll circle those. And then the last one is there's a pushing force from the ground perpendicular to the surface toward the chosen body. I'll call that N40 because it's not the same as this one. Yes?
What's the 392.4?
That is the mass 20 times 9.81 is 196.2, and 40 times 9.81 is 392.4.
So the force of it downwards is the mass.
Yeah, exactly. Yeah, where did I? Okay, so the gravitational force is always the mass times 9.81 if you're in SI units. Okay, last thing. So this is important. So when two objects push on each other, the contact forces have the same magnitude and the opposite direction. And so that's why we're going to always use the same variable. And this is a law called Newton's third law. Yes.
Then wouldn't the force that the ground is pushing back on the object that's,
Okay, so yeah, this is something that's going to take everyone a little while to get used to. But so like if you think of this force is the force on the cart by the ground. Okay? And so this rule says the force on the ground by the cart would have the same magnitude as this. But it doesn't say that the force on a different cart by the ground has any relation to the force on this cart by the ground. It's only when the two things are applying a force to each other. You know what I mean? So in this case, you know, both of these two forces, those come from the 20 and the 40 being in contact with each other. So this is the force on the 20 by the 40. This is the force on the 40 by the 20. So it's when all you're doing is switching which one is acting on which. Okay. Any other questions? Yes.
And like, correct me if I'm wrong, but I think what you were implying was that if like an object, for example, is not moving in the direction of the force, then the forces are equal. Like from the carriage to the ground and the ground to the
Well, no, that I wasn't saying that right now, although there are cases where that's true.
Okay.
So even if, no matter what's happening when these two are colliding with each other. Okay, so let's go back to the football guys. So when they collide, there's going to be a very unequal outcome, you know?
For sure.
But while they're in contact with each other, this is a really sort of surprising thing. But while they're in contact with each other, the force on the little guy by the big guy is going to have the exact same magnitude as the force on the big guy by the little guy. They're just going to be in opposite directions.
Okay.
The super unequal outcomes just come from the fact that, say that contact force on each is 2,000 newtons or something. I don't really know how big it would be. So say 2,000 newtons. Well, 2,000 newtons doesn't accelerate him nearly as much as it accelerates him.
Okay.
Okay? But no matter what they're doing, anytime two things are in contact, the magnitude of the contact force is the same and opposite direction. We'll talk about that plenty and in lab and everything. But yeah, like there are all these cases where it just doesn't seem plausible, you know, like hitting a baseball. Somebody hits a baseball 400 feet. Like, it doesn't make any sense that the ball applies the same force to the bat as the bat applies to the ball, but it's true. And the reason that the ball flies is because it weighs a couple ounces and the batter weighs 200 pounds and is connected to the ground, you know?
Is that always the case?
Yes.
When there's contact?
Always.
Okay.
Any kind of contact, that is always the case.
Yeah.
Yeah, that's Newton's third law. His second and third laws are really good. His first law is kind of lame. It's a warm-up law.
Yeah. Oh,
Okay, so anybody who had lab the week before spring break, you're off this week. Anybody? Yeah, okay. So if you had lab on Monday before spring break, we don't have anything going on today. I'll be in there if you want to talk about questions or anything, but you don't have to go to lab.
Okay.
But then we'll do the Wednesday
Yeah,
lab as
okay,
usual.
That's what.
Okay?
You're right. Right. I know, I was gonna say, you said you had lab on Monday. Yeah. I forgot that you weren't.